Somewhere in the universe, right now, there is a clock ticking more slowly than yours. Not because it is broken, not because of any mechanical fault, but because of where it sits in the fabric of space-time. Closer to an object so massive, so dense, that the very flow of time bends around it the way light bends around a lens. That object is a black hole. And the strange truth, the truth that took humanity centuries to even begin to grasp, is that time is not a constant. It never was. It is a river, and gravity is the terrain through which it flows. Where gravity deepens, the river slows. This is not metaphor. This is physics. We're accustomed to thinking of time as the one thing that stays the same. Distances can stretch. Matter can transform. Energy moves and shifts and changes form. But time, we assume, marches forward at a single, reliable pace for everyone, everywhere. That assumption is wrong. And the proof of that wrongness is not locked away in some abstract equation on a chalkboard. It is measured. It is tested. It shows up in the GPS satellites orbiting above your head right now. Satellites whose clocks must be corrected daily because they tick at a slightly different rate than clocks on the surface of Earth. If those corrections were not made, your navigation would drift by several kilometers every single day. Time dilation, the slowing of time by gravity, is not a thought experiment. It is an engineering problem we have already solved. But near a black hole, the effect is not slight. It is not a matter of microseconds per day. Near the event horizon of a stellar mass black hole, time slows so dramatically that an observer watching from a safe distance would see someone falling toward that horizon slow down, freeze, and, in the most haunting image in all of physics, never quite arrive. Understanding why this happens and what it truly means requires us to rethink the nature of space, time, and gravity from the ground up. So let us begin. Before we can talk about time slowing down, we need to understand what time actually is, or at least what our best physics tells us it is. For most of human history, time was considered absolute. Isaac Newton, one of the greatest minds in the history of science, described time as flowing uniformly, independent of anything external. It was the backdrop against which the universe played out its drama, immovable, unchanging. Then, in 1905, a young patent clerk in Bern, Switzerland, published a paper that quietly dismantled that view. Albert Einstein proposed something radical. He said that time and space are not separate things. They are woven together into a single fabric, what we now call space-time. And crucially, the rate at which time passes is not fixed. It depends on how fast you are moving, and it depends on how strong the gravitational field around you is. The first part of this, time slowing for moving objects, is called special relativity. The second part, time slowing in gravitational fields, is called general relativity. It is general relativity that concerns us tonight. You have likely seen the image before. A heavy ball placed on a stretched rubber sheet, creating a depression, a well. Smaller objects placed on the sheet rolled toward the heavy ball, not because it is pulling them with invisible strings, but because it has curved the surface they travel on. This is the classic visualization of how mass curves space-time. It captures something real, but it also misleads in one important way. It shows only the bending of space. It does not show the bending of time. And in truth, for objects moving at ordinary speeds, like planets orbiting stars or you walking across a room, the bending of time contributes far more to gravitational effects than the bending of space does. Gravity, in its deepest sense, is not just a curvature of space, it is a curvature of space-time. And a massive object does not merely warp the geometry around it, it warps the flow of time itself. Let us do a thought experiment. Imagine two identical atomic clocks,
the most precise time-keeping devices we have, accurate to within a second over billions of years. We place one at sea level, at the base of a tall mountain. We carry the other to the summit. We let them run for a year. Then we bring them back together and compare. What do we find? The clock that spent the year at higher altitude, farther from Earth's center of mass, in a slightly weaker gravitational field, has ticked slightly faster than the clock at sea level. The difference is tiny. We are talking about a few microseconds over the course of a year, but it is real, and it is measurable, and it has been measured, most famously in the Hafele-Keating experiment of 1971, when physicists flew atomic clocks around the world on commercial aircraft and compared them to stationary clocks on the ground. The clocks did not agree, and the disagreement matched exactly what Einstein's equations predicted. The deeper you sit in a gravitational well, the closer you are to a massive object, the more slowly time passes for you. This is gravitational time dilation. Now, let us take this logic and push it to its extreme. A stellar mass black hole, formed when a star perhaps 20 or 30 times the mass of our Sun collapses at the end of its life, packs that enormous mass into a region perhaps 30 kilometers across. The gravitational field near its surface is not merely strong, it is incomprehensible by ordinary standards. At the center of this object, or at least at the region we call the singularity, our known laws of physics break down entirely. We do not claim to know what happens there. The mathematics produces infinities, which is physics telling us it has reached the edge of its own applicability. But we do not need to go to the center to find something extraordinary. We only need to approach what is called the event horizon. The event horizon is not a physical surface, it is a boundary, a threshold in space-time beyond which the escape velocity, the speed you would need to reach to break free of the gravitational pull, exceeds the speed of light. Since nothing we know of travels faster than light, nothing that crosses the event horizon can return, not matter, not radiation, not information of any kind.
Now imagine two travelers. Call them A and B. Traveler B remains at a safe distance, watching. Traveler A descends toward the black hole in a spacecraft. As Traveler A descends, B watches through a powerful telescope, and something strange begins to happen. Traveler A's clock, as seen by B, begins to run more slowly. Traveler A's movements slow. Their heartbeat, if it could be observed, would slow. Every physical process in Traveler A's frame of reference, as seen by B, begins to decelerate. As Traveler A approaches the event horizon, this effect becomes more and more pronounced. From B's perspective, Traveler A appears to slow asymptotically, approaching stillness but never quite reaching the horizon. The light coming from Traveler A's spacecraft is also stretched to longer and longer wavelengths, shifting first toward red, then infrared, then radio waves, then beyond detection entirely. To Traveler B, Traveler A appears to freeze at the edge of the event horizon and slowly fade from view. But here is where the story becomes genuinely strange. From Traveler A's own reference frame, from inside their own reference frame, nothing unusual happens at the moment of crossing the event horizon. There is no wall, no barrier, no flash of light. If the black hole is large enough, the tidal forces, the difference in gravitational pull between one side of the spacecraft and the other, might be barely noticeable at the horizon itself. Traveler A simply crosses, and time, from their perspective, flows normally. They continue to age, their clock continues to tick, they breathe, they think, they experience the passage of moments exactly as they always have. What has changed is not their experience of time. What has changed is their relationship to the rest of the universe. They have entered a region of space-time from which no causal signal, no message, no light, no gravitational wave can reach the outside. They are not frozen, they are simply elsewhere,
in a region of spacetime permanently disconnected from B's future. This is one of the most disorienting truths in all of physics. Two observers watching the same event, the crossing of an event horizon, have completely irreconcilable experiences. Neither is wrong, neither is in error. They simply inhabit different regions of spacetime, and what is simultaneous for one is not simultaneous for the other. Time is not a single river, it is a landscape of rivers, and each observer travels a different path. There is a common misconception about black holes that is worth addressing directly because it shapes how many people think about them. The misconception is this, that a black hole is simply a place where gravity is extraordinarily strong, that it is essentially a cosmic vacuum cleaner, sucking in everything around it. This is incorrect in a subtle but important way. A black hole does not have more gravity than the star that formed it. If our sun were somehow compressed into a black hole, which it cannot be, it is not massive enough, but as a thought experiment, the planets would continue to orbit along precisely the same paths they do today. Earth would not be sucked in. The gravitational influence at a distance would be identical to what it is now. What a black hole does is concentrate mass into a region so small that you can get extraordinarily close to it. And it is proximity, not some magical extra force, that produces the extreme gravitational effects. The event horizon exists not because the gravity is different in kind, but because the density is such that the region from which escape is impossible has grown to a size you can actually reach. This matters for how we think about time dilation. The slowing of time near a black hole is not caused by some exotic property unique to black holes. It is caused by the same gravitational time dilation that causes clocks at sea level to tick slightly more slowly than clocks on a mountain. The principle is identical. The scale is simply pushed to an extreme that has no parallel elsewhere in our ordinary experience. The universe is not operating on different rules near a black hole. The same rules we can measure, test, and verify in a laboratory on Earth extend all the way to the most violent and extreme environments the cosmos has to offer. That consistency, that deep, persistent regularity is perhaps the most profound discovery in the history of science. There is also a second truth worth sitting with. We often speak of the event horizon as if it is a place of violence, a point of destruction, a cosmic death sentence. And for a stellar mass black hole, where tidal forces near the horizon are enormous, that is approximately correct. If you were to fall into such a black hole, the difference in gravitational pull between your head and your feet would be so extreme that you would be stretched. Physicists with a certain dry humor call this process spaghettification. But for a supermassive black hole, the kind that sits at the center of a galaxy with a mass of millions or billions of suns, the event horizon is so large that the tidal forces at that boundary are actually quite mild. An astronaut crossing the event horizon of a sufficiently large black hole might not feel anything unusual at all in the moments of crossing. The doom is not at the horizon. The doom is in what lies beyond it, the inevitable trajectory toward the singularity, from which no future path in spacetime leads outward. But at the moment of crossing, for the right black hole, there is only silence and starlight bending. Let us step back now. Let us allow the mathematics to rest for a moment and simply contemplate what we have encountered. We live our lives under the assumption that time is fixed, that a second here is a second there, that the age of the universe means something universal, that 13.8 billion years of cosmic history is a single number, true for all observers everywhere. It is not. Depending on where you have spent your existence, deep in a gravitational well or floating in the relative emptiness of intergalactic space, you might have experienced significantly different amounts of time since the Big Bang. The universe does not have a single master clock. It has an infinite number of clocks, each ticking at its own rate, each measuring a slightly different elapsed time since the beginning. This is deeply strange, and it is true.
For most of us, most of the time, the differences are negligible. We live in a region of space where gravitational fields are relatively weak by cosmic standards, and the clocks of our daily experience agree with each other to extraordinary precision. The sun's gravity slows Earth's clock slightly relative to a clock floating in deep space, but the effect is small. Our intuitions about time work well enough for the world we navigate. But the cosmos is not obligated to remain within the bounds of our intuitions. Somewhere in our own galaxy, at a distance of about 26,000 light-years toward the constellation Sagittarius, there is a black hole 4 million times the mass of our Sun. It is called Sagittarius A-star. In 2022, the Event Horizon Telescope collaboration published the first image of it, a ring of glowing gas surrounding a dark shadow, a direct visual record of the boundary between the knowable and the unknown. Near that boundary, time flows at a measurably different rate than it does here. The effect is not enormous at the distances where gas and stars orbit Sagittarius A-star. Those objects are typically far from the event horizon itself. But at the horizon, the dilation would be extreme. A clock placed just above the event horizon and somehow sustained there would tick with agonizing slowness relative to us. In the time it took that clock to tick once, billions of years might pass in the universe outside. This is not drama, this is geometry. And it forces a question that I find worth sitting with. If time itself is flexible, if it can be stretched and compressed by the presence of mass and energy, then what exactly is time? Is it a fundamental feature of reality, or is it something that emerges from deeper physics we have not yet fully grasped? Is there a level of description at which time simply does not appear, where the equations are timeless and the flow we experience is in some sense an approximation, a local feature of a particular region of space-time? These are open questions. Serious physicists hold different views on them, and the honest answer is that we do not yet know. What we do know is that the universe is stranger and more intricate than our ancestors imagined. What we do know is that a man working largely alone with a pen and paper and an extraordinary capacity for geometric intuition worked out the structure of space-time over a century ago, and that his equations continue to describe correctly every gravitational phenomenon we have tested them against, from falling apples to colliding black holes sending ripples through the fabric of space itself. And what we do know is that you, sitting here in this moment, are subject to gravitational time dilation. Your feet, slightly closer to Earth's center of mass than your head, are aging slightly more slowly. The difference over a human lifetime is measured in nanoseconds, but the principle is real, and it extends from your feet all the way to the edge of a black hole's event horizon, changing only in degree, not in kind. You are, in a very literal sense, a participant in the physics we have been discussing. There is an image I return to often. Imagine a being, not human, but something with a long enough lifespan and the right kind of technology, who could place themselves in a stable orbit just above the event horizon of a supermassive black hole. Not crossing it, just hovering, sustained by enormous thrust in the extreme curvature of space-time just outside the boundary. They hover there for what, by their own clocks, is only a few years. Then they leave. They travel back to the galaxy they came from. What they find is unrecognizable. Civilizations that were young when they departed have risen and fallen. Stars that were burning when they left have died and become remnants. Millions of years, perhaps more, have passed in the universe outside, while only a handful of years passed for them. They are travelers not just through space, but through time,
not because they moved fast, but because they sat still in a deep well of gravity and let the universe age around them. This is what the physics tells us is possible, not in principle, in fact. Time is not the background. Time is not fixed. Time is a participant in the universe, shaped by the matter and energy that inhabit it, inseparable from the geometry of space, bending and stretching and pooling in the valleys carved by the most massive objects the cosmos has produced. And perhaps the most quietly astonishing thing of all is this: we know this. We, a species that has existed for a cosmically negligible fraction of the universe's history, on a small rocky world orbiting an unremarkable star, have worked out the curvature of time itself. That is not a small thing. Sit with that for a moment.